about experiments. So I hope I won't bore the theorists too much, but I do have equations. I hope I understand them. So I will first give you a bit of some introduction to this technique that we've been using for many years now, that we think is really appropriate to characterize soft materials in general and biological soft materials in particular, and more recently also active biological materials. And that technique we call it microrheology, which is of course related to typical macroscopic rheology that people use in mechanical engineering or material science. But the micro, I'll show you what it means and why that's appropriate for biological systems. But the sort of last wrinkle that I want to then focus on is a particular sort of new development that we've been playing with, namely using not just beads, which are usually the probe that you put into cells or that you put into a system to do microrheology, but we actually look at filament fluctuations. And I'll tell you why that is interesting and why what the advantages are. And of course, in the spirit of this conference, I'll show you mostly non-equilibrium results or results in active materials. This is forward, no, probably not. So, so in the end, of course, you would like to understand something biological as complicated as a developing embryo, which has obviously sort of highly advanced program for making, transforming that single egg cell that is the start of the whole story into a larva and finally into a fly. So that's kind of one of the holy grails of developmental biology nowadays, but also biophysics is getting a foot into the door, trying to understand the physical processes that are going on there and sort of collective cell dynamics. We've heard quite a bit about that, of course, in this meeting already. And what is also difficult to get to, if you think about physics, are first of all the forces. So what you see is usually displacements, but in order to get to learn anything about the stresses and forces in these systems, we need to know something about the material properties, because you can't directly see the forces. You can only see displacements, but you can see strains, but you can't see stresses. So it's necessary to characterize the material properties, but they can be very complex because the system is usually non-homogeneous. Even a single cell, of course, is highly inhomogeneous, and can be also some large deformations and nonlinear responses, and then the whole 9 yards. So it's a pretty big challenge. And in addition, of course, in an embryo like this, the fly embryo is sitting in an eggshell, in a fairly tough shell. Right? So it's very hard to get in there. You can inject stuff, but then you can also, typically, it's very easy to destroy the embryo. But I'll show you one method where, actually, no, I'm not going to talk about that, but it turns out you can also get it out of the eggshell. And so in collaboration with Dan Keyhart's lab at Duke, we also do experiments on these living embryos once you peel them out of the eggshell. But actually, I'm not going to talk about that part. It would be too long for today. But this is sort of the final idea of what we want to achieve. We want to learn about material properties and then, of course, forces and stresses and how the physics of these cell movements actually work. And of course, you can do that on a macroscopic or mesoscopic level. You can then write hydrodynamical equations and then sort of gloss over the macroscopic details as a first approximation. But in the end, you really want to learn something about which molecules are doing the job and how are they controlled and who are the motors and who are the force load bearing elements and so forth. And so that relies, of course, heavily on biochemistry and also on imaging methods. So this is these great videos that my collaborator Dan Keyhart at Duke has taken at the Janelia farm. So they looked at a process that's called dorsal closure, which is one of the sort of mid-stage events that happens in the development of the Drosophila embryo. There we go. That's the projector again. I didn't step on anything, but so I'm going to stay away from that.
You have to dance around that.
Yeah, I'm going to stay far away from it. So dorsal closure, actually, I should have shown you the preceding video. Is what happens pretty much, I mean, at the end of this movie. So this is the germ band extension, and then it's the process called germ band retraction, which is when this part moves back. And this kind of opening that's left here, that's the dorsal opening. And now you see the dorsal opening filled with the so-called amnioserosa cells, and that contracts and the cells disappear. And that process is called dorsal closure. And so Dan's lab has been working on that for a long time. And they've learned a lot of details, of course, about the molecules and all these different force-generating elements and so forth. There's lateral epidermal cells, there's amnioserosa cells, there's an actomycin-rich so-called purse string that contracts and so forth, like in wound healing. But in the end, I just want to show this to emphasize the sort of the pathway of going down to the molecular level. So here you see already, this is the actin labeled. So you see lots of interesting kind of structures like these filopodia that are sticking out near the cell boundaries. And then here you see the edge of the cells in the side view has a lot of actin. There's myosin also, and that contracts. So in the end, of course, we would like to learn how all these things work together. And in this paper from a couple of years ago, in this large collaboration with people at Genelia, including Eric Betzig and Jennifer Lippmann-Schwartz, and here we go. Looked at this process and sort of zoomed into the amnioserosa while the process was going on. And they used a structure delineation, so one of these super resolution methods, in a combination with turf. So it's like a surface constraint. They slap the embryo upside down on the glass surface and then use total internal reflection, leaky, sort of close to total internal reflection to get a little bit of light into the first layer. And that way they can see single actin filament. So you see a cell is about, you can sort of see it's a unit that contracts. This is one cell, here's another cell roughly. And you actually see bundles and also some filopodia that are sticking out here towards actually the glass in this case, but you also see single actin filaments in these networks, but we can resolve actin filaments in these cells. And you can see that these actin filaments contract like here. That's driven by myosin, which is not labeled here. But this is getting us to the sort of molecular level, and we can characterize these actin networks, and we know something about the motors, and so that's in the end where we want to get to. But let me start a bit more with the basics first. Many of you might know that, but just to get everyone in the same wavelength. So microrheology is basically doing rheology on a small scale, on a scale that's compatible with doing work in cells, for example. So this is a video. So either use thermal fluctuations. So now you see that, well, now it's what we call active microrheology. Now there's an optical trap pulling on this thing, but in between, passive Brownian motion. The gel is fairly soft. You don't see the actin here. It's 1 mg per mil, 1 milligram per milliliter actin, filamentous actin. So it's sort of entangled, not really cross-linked. And that bead is doing Brownian motion just driven by thermal excitations. And you can use that to calculate, to deduce the environment, the shear elastic moduli of the environment. But you can also do that in an active way. You can turn the optical trap, there's an optical trap that you don't see. So there's a laser focus, infrared laser focus on that bead. And if you just use low power and just sort of monitor the fluctuations, we do what's called passive microrheology. But if you turn up the power and pull on that particle with the optical trap, we can do active microrheology. We can do that in a frequency dependent way by oscillating this the position of the optical trap with an acousto-optic deflector, which you can do up to 100 kilohertz or so easy. So the advantage very However, I think it's mine.
No, it's not. It's the one
Alright,
I'm
it's
moving
fine.
that mouse.
That's right. Okay, yeah. It's unmuted now. Do we have feedback?
No, it's
Doesn't
fine.
seem like it's unmuted now. I think it's unmuted. Okay, that's maybe a step forward. Ask her whether it works.
I'm not
Yeah.
sure how to make this.
But you
work.
but how can you, oh, you can get to the chat, so can you get to the chat? Ask her if it works. I guess she could hear us, if she can hear us, so Rosemary, can you text briefly if it works? All right, let's continue. Yeah, that's good, it's good.
Yeah, I'm
Be
trying to
careful with
get
the
off
carpet.
the chat, yeah. I'm not sure if I can make
Maybe
it.
something's on, maybe it's work. No, that's the only internet access.
I don't know how to make this. bigger.
It works. Yeah, I know, but now we want to get the image pulls. So we get that maybe to work, but now we have to get back to full screen.
It's only showing you don't have screen over there.
It sort of
No, yeah.
stopped spontaneously.
But it's only projecting this image there.
The laptop is sharing.
It's okay, we just need to get it somehow on screen. Okay. Oh, yeah, good point.
It's pretty good. Let's get rid of this thing. That screen is supposed to start before. How do you get it to light up?
Oh, yeah.
The audio seemed to have dropped out.
No, we
No, we got it back. So as Rosemary said, she can hear us.
Yeah, I know.
It reconnected, it was muted at the date or something like that.
It was someone it spontaneously dropped, just when it came back again. And
Excellent.
the first time the whole thing, yeah, this one had to be wiggled. All right. Anyway, so the point I was making is you can use spotted photodiodes to detect the light coming out of the condenser. And it turns out there's a first order interference effect that tells you where the bead is. Basically, the light scattered by that particle in the trap is interfering with the light going through from the trap. So two spherical waves are interfering, and you have to sort of calculate that correctly. There's something called the GUI phase shift that you have to take into account. But you can see that the intensity of the light shifts when the bead shifts, and that's just nothing else than momentum transfer. Now the photons transfer momentum to the bead, and then of course there's a reaction force on the photon. So if the bead is over to the left, the light gets pushed to the left here, and the bead gets pulled back into the center by that momentum transfer. So that is useful because you can then use this non-imaging. This is just imaging the backfocal plane, but you can just project the backfocal plane on the quadrant diode, and then with high resolution, high temporal resolution, track the relative displacement of these particles in that optical trap. So that was a critical technical issue to get high bandwidth rheology out of this. And so now with this active combination of active and passive, actually the way we do it is we have a infrared or near infrared laser, sometimes actually 1064 usually, and then a visible is also near infrared laser, where the 1064 laser is strong and acts as a trap, and this shorter wavelength laser is expanded and acts as a detector. It still has enough photons to give us good resolution, but it doesn't exert much force. So this one can be wiggled, and this one can be used to measure the displacement. And then we can just directly measure the response function of the particle in that medium, whatever the medium is. So we get the real part and the imaginary part of the response function directly. And then, of course, the other method, I'm not going to go into details, but the passive method relies on the fluctuation dissipation theorem. So you know that the fluctuation spectrum is related to the imaginary part of the response function, of course, KT and omega. And from that, you can calculate the G prime and the G double prime of the medium. But before that, you can directly compare, of course, if the two give you the same result or not. And if the two methods don't give you the same result, then you know you have an active system. So basically, you correct or you use the active method. So it's a bit confusing talking about active microrheology and passive and active systems and passive systems. I'm sorry, but this has established itself somehow in the field, and there's continuing confusion going on there. But you use the active method to get the response parameters of the active medium, and then you subtract from the total fluctuations that you measure. This measure in the backfocal plane and so on with the quantum diode. You know it's the sum of the non-equilibrium fluctuations and the thermal fluctuations. You can estimate the thermal fluctuations using the fluctuation dissipation theorem, sticking in this part here that you measure actively. Convoluted logic, right? So use active microrheology to measure this. You stick it in the fluctuation dissipation theorem. We calculate the thermal fluctuations that should be there, that should underlie the total fluctuations that you observe. And by subtracting this from the total fluctuations, you get the non-equilibrium fluctuations. It's clear, right? It's convoluted, but in the end, it's just algebra. So you just basically have to correct the total fluctuations, and then you get this interesting parameter that you're after, that you want to understand and characterize those active and non-equilibrium fluctuations. Now, we had this discussion about this power law stuff when Timo Betz gave this talk last week. So I want to briefly show some results on active networks that we did many years ago also. This is an in vitro system with actin, which you don't see here, myosin motors, which are the muscle activators, and crosslinks as well. And what you see here, this motility that you see here is basically all driven by the myosin. Because I could show you the control if you want later. In the control experiment where the myosin is not active, by eye you basically don't see any motion. It's a fairly strongly cross-linked gel. So all this is driven by these motors that you don't see. So here's the sketch. So there's these bipolar little aggregates of myosin that form little force dipoles. They interact with actin filaments, contract the actin filaments locally, and then let go again. So you get these pulses of contraction. And since the network is cross-linked, it doesn't cause any phase separation, any macroscopic structure. So when you do that and first check in the absence of motors, if the two methods, the active and the passive, agree, which they should, you plot the imaginary part of the response function and you compare that with the power spectrum with the appropriate multiplications here, you see that they actually do agree over many orders of magnitude, more or less. This is the log scale. Of course, there's very large errors here, always hidden in the log scale. But that's fine. And actually, there's two sets of curves. So if that's a sample that doesn't have myosin and the other sample does have myosin in ATP, but we have a high ATP concentration, which this is a technical issue with motors. But if you have high ATP and fairly small aggregates of myosin, they're what's called non-processive. So they can't hang on, they can't produce large displacements. But when the ATP runs down, then what's called the duty ratio of the motors goes up, and then they can actually hang on and start pulling. And we also did that, of course, with low ATP concentration to begin with, but then you have to stabilize it. So it's all technical details. But what you see in the end, if you look at the system where the motors are active, you see at low frequencies a large difference between the expected spectrum from the active method and the actual fluctuations. And this part is the non-equilibrium part. And then you can take a closer look at that. So I'm not going to go into much details about the rest of this paper, but there's also, I'll show you in a moment, this discussion or something relevant for that discussion we had about the slopes of that active part. But I'm going to show that in the context of data that we took with cells, because the first experiment I showed you was an in vitro system with in vitro produced actin filaments and then isolated by myosins, and they were just put together in the sample chamber. This is the real thing. So that's the cell, the fibroblast. And we have in this case now 2 optical traps and 2 beads attached to that. And this guy is pretty active, so it's trying to eat the beads, and and this is usually these things, I should say that usually these things are sped up. So these movies, if you look at them live, are much slower. So this is probably 20 times, 50 times or so sped up. I forgot to look up the exact number. But you see there are large fluctuations, and you can follow these fluctuations. And if the cell is a bit more tame and doesn't do this crazy stuff, then they're quite reproducible. And then you can analyze that, use that whole machinery. You can analyze the active part. And so I'm skipping the intermediate steps. But if you focus on that the power spectrum of the non-equilibrium part of these fluctuations, you also find this power law again that Timo was saying last week. He doesn't understand it, but I think it's all the same in many experiments that people have done. There's a fairly simple model for that, which I want to briefly mention. But in the power spectrum, you see a slope of minus omega to the -2. In the mean square displacement, you see a slope of +1, and in the compliance, you see a slope of -1. So it's just different ways of plotting it, but it's the same thing. And the simple model for that is actually going back to work by Alex Levine and Fred McIntosh, and also Andy Lau. Can I get rid of this thing? There's Andy Lau and Tom Lubensky's lab also did some work 2003, earlier than Fred's and Alex's work. But the idea, the very simple model in this case that seems to work to explain this kind of universal dynamics in cells and tissues is based on randomly distributed, randomly acting force dipoles. These myosins can pull, and it turns out the myosins are the strongest motors in cells. So there's all sorts of other activity, but really when myosin is there, what you mostly see is the activity of myosin pulling on actin. And you can model that as a sort of step function with a finite correlation time. So in real life, of course, the stress builds up slowly and then suddenly releases catastrophically. But if you model that in a simplistic way, it's just a step function with a finite correlation time. And then assume you have these force generators distributed, in your medium, and they sort of act randomly. Then what you get in the end is a random walk in force. So not a random walk in space, but a random walk in force. And so mean square displacement has a slope of 1. Well, mean squared force, has a slope of 1, acting on some particle or whatever you have, what you're looking at. And that, of course, generates motion, and the motion it generates depends on the compliance of the surroundings. Right? So this is the force spectrum. What is the surroundings in cells? Well, that's fairly well studied. So you have Ben Fabry in Jeff Fredberg's lab, for example, way back, did a lot of experiments, and it's pretty well established that cells act like rubber balls at intermediate frequencies. So at very low frequencies, they can flow and adapt and all that. At high frequencies, they have viscoelasticity that goes up with some power law, but at low frequencies, and we're talking about 0.1 to 10 hertz or so, they have this what's called weak power law or elastic plateau behavior, soft glaciology. There's all these theories out there, but basically it's almost flat with a power law exponent that's somewhere 0.1 or 0.2. So if you put that in the denominator of the equation, where this is the driving force from these dipoles, here's the response of the medium, you get the displacement, and after some calculation, you can find out that the measurable quantity, which is the displacement, the mean square displacement as a function of time, should actually scale like time to the power 1 with a small correction factor, so 1.4, 1.3, 1.4. And that is, I think, is up to date is the best explanation for this universally observed power law behavior. There's actually a lot of confusion in the field, especially when people come more from the biology side. They see, they say diffusive, super diffusive, subdiffusive when they characterize mean square displacements. Now, that's confusing because diffusive kind of implies thermal excitation and not just the slope. So that's the first level of confusion. But in cells, when you see a power law where the mean square displacement scales with the time like power 1, people say, oh, that's diffusion, and that's regular diffusion. But it turns out when you turn the power off, so if you take the Misons out, it falls way down. So it's not regular diffusion, it's active. And it just so happens that the active, with these force dipoles and so on, the active mean square displacement is very similar to the mean square displacement of a freely diffusing particle in a viscous solution. But that's not what you have in cells. You have in some parts of the cell it might be viscous, but in the cytoskeleton it's certainly elastic and has a flat G prime, or flat G, or G prime mostly, actually, I should say. And the slope is still 1, or a little bit more than 1. So that has been confusing and still is confusing.
Sorry, I'm also confused.
Okay.
Legal processes with these force by force with the time correlation, then coupled to an overground elastic or something more complicated.
It's basically elastic, so the damping is almost negligible. And in the plateau, you typically have the G double prime dipping down. So the viscosity is much smaller. The G double prime is much smaller than the G prime in that regime. So it's just a rubber ball excited by these having all these little force dipoles inserted in it.
And at that scale, the inertia is irrelevant.
Inertia it's all low Reynolds number. Absolutely, yeah. So inertia is totally irrelevant. You can think about it as a step. If you take a step in force and Fourier transform that, you get 1 over omega.
Yeah.
If you take the square of that, you get 1 over omega squared. It's as simple as that. Because we assume these steps. So we don't have delta functions, but we have steps of a finite duration.
I understood. Yeah, I understood that after later.
Okay. Okay, so that was a little excursion, but I want to get to the filament. So one thing you also saw already are flagella and cilia. So this is a beating flagellum isolated from chlamydomonas that Isabella talked about yesterday. So you can torture these chlamydomonas, they chemically, so they let go of their flagella, and then you can demembranate the flagella, and if you have ATP in solution, they actually start beating, keep beating for a while. This is a high-speed movie that was actually taken at Woods Hole. So the Woods Hole MBL physiology course is where everything happens. And so my postdoc at the time, Nick Napachi, who's now at MIT, was there, and Jahort was there, and then his postdoc, and they looked at these flagella. So the interesting thing about that is that looking at these organelles or these active flagella, you can learn quite a few things. You can learn or try to learn something about the forces that drive them. But what I want to more focus on is you can also learn something about the environment. This one is just fluctuating in solution in some buffer. So there's nothing interesting, nothing viscoelastic or so in the environment. But I focus more on using filaments as microrheology probes. So you can learn about the activity, you can learn about the elastic properties of the filaments, and you can learn about something about the embedding environment. Just as a small remark, if you want to look it up later. So we used that beating flagellum to look at non-equilibrium. So we together with Chase Bruders and Brad McIntosh and Nick we looked at detailed balance and the breaking of detailed balance. So if you do a mode decomposition in dynamic normal modes of this filament, and then plot construct a phase space that has one mode on the amplitude of one mode on one axis and the amplitude of another mode on the other axis, and then plot a phase space trajectory. In this case, in this very clear non-equilibrium case, you get circulation in phase space, and that is, of course, the same as broken detailed balance. So that was a different story. I don't want to get deeper into that, but that's another nice way to check if a system is in non-equilibrium, sort of a red flag approach. If you see that happening, if you see circularity in flux in the space, then you know it's a non-equilibrium system, or the process that you're looking at is non-equilibrium. But this is a side remark. So we did experiments more recently with carbon nanotubes, so passive filaments. They're just dead carbon. They come out of course, Rick Smalley and Bruce Weissman's group at Rice. Smalley the Nobel Prize for buckyballs and these structures, and of course graphene sheets are related to that. So these are simple inorganic filaments, the tubes. They can get very long. So this is a movie of about 5 micron long one, but they can get 10 microns long or longer. And they have a very small diameter, only about a nanometer, depends on the chirality. And some of them, not all of them, are semiconducting and are infrared fluorescent. And that's very useful for us, because we use them as fluorescent probes, but also as mechanical probes. So this one here happens to be embedded in a solution of hyaluronic acid, which is a viscoelastic solution, more viscous than elastic. It just, we use it as a model system to study or to develop the method how we can use these fluctuations to now measure the viscoelasticity of the solution. In this case, the bending elasticity of the nanotubes is fairly well known. So we use that knowledge basically to extract knowledge in the microrheology sense about the medium. And of course, the driving force here is just thermal fluctuations. So there's no active force in this case. And so it's fairly straightforward. But the advantage of using a structure like that, I mean, these have extremely high aspect ratios, like 10 to the 4 or so. So they're very thin. And they can get into anything. They can get into the cortex of cells. They can get into the nucleus. So they don't perturb the biological system, but they also get in very tight, like agarose gels or so, where you have a small mesh size, where it's not so easy to have beads or maybe you can do nanometer beads. But in many places in biology, it's hard to get probes into the system, or they get expelled. Like in the mitotic spindle, if you try to put beads in there, they get pushed out. So these guys are kind of stealth probes. And of course, the other advantage is you get information about multiple length scales. With these beads, we have the bead as a length, the radius of the bead is a characteristic length scale, and we can't see anything smaller that basically probe the response of the system on length scales smaller than the bead size. But here we have modes, and the high modes probe small length scales, and the long modes probe large length scales. So that's an advantage of using these filaments, apart from the fact that they're stealth. And this is a fluorescent spectrum. This goes back to Rick Smalley and Bruce Weissman's papers in the early 2000s. And Nikta, actually, when she joined the lab as a postdoc, brought the nanotubes to the lab and the technology. And we bought a bucket of nanotubes, a 4-gallon bucket, for a price that's more than an American minivan. But it is a lifetime supply. So it was a couple of grams, like 2 grams or so. I don't know, but it's this much. So it's very light. It's like soot, very, very fluffy. And so we have lots of those. So this is annoying that it obscures the bottom of the slide. Wasn't there a trick to avoid that?
Probably is. I don't know where.
We had that before, right?
That's fine, yeah, but,
view thing, or
Maybe you know the escape button, press the escape button once, then it goes up the.
no, I mean, escape sounds dangerous, but move the.
If you go to view options at the bottom, yeah, but there should be like a buy or sell thing.
Down at the bottom screen, right? View options, I guess, yeah. Yeah.
There should be a high video,
That's
high video panel, try that.
looks good. Left button or the right button? I didn't do it.
So go back in there.
Or is it on my screen? No. Oh no, this is not on my screen here, right? This is
Yeah, if you go to the bottom of the laptop. Oh, yeah, it has to be on the bottom.
Yeah, I did go there and clicked and do anything.
Yeah, it's already, you can go to more at the bottom, I don't know.
There was a high video
Yeah, you already
thing,
did.
but it's already. Anyway, let's keep
There's
going.
also view at the top, at the very far, right corner.
Oh, this one?
You did the other option. Click on it, but
Okay, let's see, it's really small there. Standards.
it's already on full screen.
Show itself. Yeah, doesn't seem obvious.
But anyway, I mean, is there another line below this one, the correlation function, is there another line below the correlation? Because that is.
No, it's just that's the last line, but. You mean on the slide?
Yeah, on the slide.
No, that's the last one. You can sort of see it, but not
Yeah.
very well.
Okay.
Yeah, I guess I'll have to just keep going. So, Kengo Nishi, a postdoc in the lab now in Duke, started in Göttingen before I moved, has developed this method. And so, what you have to, how you set it up is you think about the forces acting on a filament that's embedded in the viscoelastic medium. So those forces, then you write down an automatic equation for an element, so force per unit length, consists in the time domain of a memory function. So that's the viscoelastic response of the medium. The alpha is the memory function. U is the displacement, the lateral displacement of the filament from a reference line that's connecting the ends. You have the bending elasticity. So that's just the bending modulus of the filament, with a curvature dependent restoring force. And of course, you have a Brownian term, a noise term that is connected to, that's the last line here, that's connected, of course, by fluctuation dissipation to the response function to make FDT work. So that's the Langevin equation, or equation of motion in the time domain. There are these are the definitions. And then, now we have to kind of evaluate that for these filaments. So the first thing we do is we expand the filament shape into dynamic eigenmodes. And these transverse deflection eigenmodes, this goes back to a paper of Sergio Aragon and Bob Pecora in the 80s when they were working on DNA dynamics. It's just a slightly complicated hyperbolic cosine and sine and so form that takes into account that the ends are free. If it's a continuous filament, you can do sine and cosine, but if it's a filament with open ends, you have to do a slightly more complicated form of the eigenmodes. And there's a wave number, of course, and since we're looking at filaments of different lengths, we want to plot things in terms of the actual wave number, which is related to the mode number, and then of course the length of the overall contour length of that particular filament. And so first mode, second mode, third mode look like you expect them to look like. So once we do that, or actually before that, we can write, of course, now the Langevin equation for a particular mode. So again, we have the memory function from the viscoelastic environment. We have the bending, the restoring force here, and the noise. Now, we assume linear response, so small fluctuations. We can express the amplitude, the amplitude of the bending mode by response function acted on by the Fourier component of the force that's acting on the system. So the Brownian force in this case. And then, of course, from the expression from the Langevin equation, we can write this response function in terms of the bending modulus and the alpha, not to be confused with A here, that's very similar, but alpha is again the memory function, the Fourier transform of that memory function. And so that now, of course, we want to ultimately relate to the shear elastic modulus of the medium. So there's one more step. This Fourier transform is proportional to the memory to the complex shear elastic modulus with the geometrical factor, of course. That's for beads, it's the radius and so forth. A piece of filament is just basically the length divided by the log of the length divided by the diameter. And this effective length is basically the wavelength of one of these modes. And so it's related to the wave number. So it gets shorter and shorter for the higher modes. And that gives you that multi-scale approach. Of course, it's not a huge scale range that you can test, but like factor of 2 or 3 or 4, so with the higher modes. So that's the way to evaluate those data. And then, of course, some practical issue is how do you do that? I mean, I wasn't going into the details. We used to use Kramers-Kronig relations to first get the imaginary part and go to the real part, but it has some disadvantages. It makes it asymmetric. So what's easier or what's better experimentally is to use time-dependent mean square displacement for the amplitudes, and then you have to take a derivative of that. So that makes it a bit tricky numerically. You have to be careful about how you do the derivative. But when you do that, you get more symmetric results. But in the end, that's the way we evaluate the data. Of course, this mean square displacement function is just the difference between the amplitudes compared to the resting amplitude, or the starting amplitude. Like this is a correlation function, and then we can plot that and evaluate that and calculate the G prime and the G double prime, and get done with that. So now, how good is that? So here is, and this was a test solution with a hyaluronic acid. So we knew the viscosity of that system, and we could also, of course, measure it independently with standard microrheology. So here you see the first 3 modes of a 5 micrometer long carbon nanotube, which I think was the one or was very similar in length to the one I showed you the video of. And so you see the long wavelength modes fluctuate more, as you expect from the excited system, for a bending elastic filament, and the higher modes fluctuate less. But you can record pretty well by just tracking them in video. And of course, in this case, you're limited by video rate, by video frequency. But you can track the amplitudes as a function of time. Here, of course, already evaluated amplitudes as a function of time. And then this is the mean squared amplitude difference. And you see how it, the functional form of that. Obviously, it levels off because of the finite bending elasticity. It takes a lot of energy, of course, to bend these filaments. And the higher the mode, the more energy it takes. So the ones that have the short wavelengths don't get excited as much, and the long wavelengths have larger amplitudes. And at short times or high frequencies, that's when you begin to see, or mainly see, the response of the medium. And so this response is divided basically in 2 areas. Here you see the medium. Here you see the filament. Okay, so also you want to check on the spectrum of these mode amplitudes, and you expect something like a q to the -4 slope here, which I didn't put the slope here, but it should be q to the -4. You can see here, lots of magnitude here, and it's pretty close. So that's within the noise range. So that seems to work fine in this equilibrium system, and gives us this additional, it gives us a stealth probe, and gives us that sort of multi wavelength, multi-length scale microrheology probe. But now, okay, here's some more data on the G prime, G double prime. I haven't shown you the final results. So here's a bunch of different solutions here, starting. Well, this is the lower concentration here, higher concentrations. I guess the main thing is it's a very weak viscoelastic solution, so only 0.1 or so Pascal, which is it's quite soft. So in the macroscopic rheometer, it's very hard to measure these things. But we compare it here with conventional microrheology using beads, which we know very well. So those agree. But you also, of course, see there's pretty large error bars on this log scale. Right? So all this microrheology has fairly large error bars, and some people try to hide that by functional fitting. I don't want to mention names, but then the curves look very, very smooth. But the real curves always have quite noisy. And the G double prime tends to be smoother, but this is sort of a comparison, and it shows consistency between the established method and this filament method. So that's reassuring. So now we can actually go ahead and use that for something else. Actually, one other sort of trick that Kengo figured out, Kengo Nishi, the postdoc who did all this, he thought about sort of global fitting, and he used all these curves for different Qs, for different wave vectors, and put them in this plot, and then fitted the whole thing with a sheet, with a 2-dimensional fit function. And that, from what I showed you before, that 2-dimensional fit function has a couple of parameters. It has the viscoelasticity of the environment, it has the bending modulus, and actually only these 2. But if you stick in if you stick in the independently measured viscoelastic response of the hyaluronic acid, then this whole thing can be used to fit for the bending elasticity of the nanotubes. But it's a lot of data that can fit with this global function, and this has only one parameter. And you can see the black lines are the intersections of the blue fit plane with at the respective Q values, and you can see it fits the data quite well. The sort of both capturing the shape, the different shapes of the functions and the amplitudes. And that gives us a pretty good estimate for the bending stiffness, which of course was known before, but they just wanted to check if it's consistent. And I guess you can barely see it. So we find about 7 × 10⁻⁶ blue meter, and actually Nicola Fockley in her PhD thesis with Matteo Pasquali at Rice measured this for fluctuations, and she had 1.2 × 10⁻26. So it's pretty close. Actually, sorry, I think it was 10⁻25. So this verse was larger. So, but it's within a factor of 2. So that is just all of that was to validate the method. So I want to show you in the very end some very recent application of this method to cells, to non-equilibrium systems. We looked at microtubules, and of course you have heard a lot about microtubules. Microtubules are fairly rigid filaments, and if you look at them, they have a persistence length of something like 1 millimeter. So if you look at them in the microscope, they fluctuate a little bit, but not very much. But in cells, they fluctuate a lot. And that's because of the forces that the cells exerts on them. And that's mostly coming from myosin again, pulling on actin, and the actin go all around the microtubules and then bends the microtubules. So this is unpublished by this, we were looking at the last version with Fred last week, so it's almost out. Not accepted, of course, but the idea was to now look at microtubule bending. And of course, the idea behind that is to use filaments that are native to the cell. So we don't introduce anything, neither beads nor filaments nor anything, no artificial probes into the cell, and just use the existing filaments in there and try to basically hijack those filaments and their fluctuations to learn something about both the filaments and the viscoelastic embedding and the forces. So we basically have three unknowns in this problem. We are partially unknowns: the bending elasticity of the filaments, the local embedding in the cytoskeleton, and of course the driving forces. And the basic message in the end is going to be, if you know one of those, you can basically measure the other two. So it depends which one you measure with a different method, and you can stick it in, and then you can extract the other two. And we do that. We look at the fluctuations in video microscopy, fluorescence microscopy, but we also use magnetic beads and what's called a magnetic tree. So it's basically just an electromagnet with a sharp tip brought very close to the cells, like a couple of 50 microns or so. And then we pull with a known force on these beads and use that as a way to estimate the viscoelasticity, to have this input parameter. So these are the cells. These are HeLa cells labeled, where the tubulin is labeled with what's called SIR tubulin. That's a Taxol derivative that's fluorescently marked. It goes into the cells. It doesn't perturb the tubulin very much, so it's a live cell stain. As opposed to, I mean, you probably have seen a lot of images of cells, but very often people kill the cells, permeabilize them, and use antibodies to stain the various components. But we want to look at fluctuations, so we can't do that. So we need live stain, and that's SIR tubulin. This is a zoom into an area where you can sort of see single microtubules. Now, of course, it's quite a mess here and here. But if you look under the nucleus, here's the nucleus, or in the periphery, you can actually resolve single microtubules in this confocal microscope. You can do much better if you use super resolution like SIM or so, but this was just a regular confocal, not even TURF or anything. So that's what he then evaluated with the same methods that I showed you before. But now we have to add one more force. So there's an active force coming, of course, from the myosin actin again, that we have to take into account. That's bending. Actually, that's the one that's really mostly bending the microtubules. The thermal fluctuations are almost negligible. So we again look at the mode decomposition, and then now have here, of course, the force including or dominated by the active force. And then we go back to the results I showed you from the cells, Alex and Fred's model, where we have seen that this force spectrum for these distributed dipoles is basically a Lorentzian. And it has this correlation time, which is 5 to 10 seconds. And of course, it has an unknown amplitude that we have to fit, we have to get out of the data. But we use this functional form as an assumption here in this method to get at the microtubules. Otherwise, the procedure is the same. I'm not going to go through that again. So we first wanted to input the viscoelasticity to get rid of one of the parameters, and then learn something about the bending stiffness and the forces. So that's why we use the magnetic beads. So this is showing this experiment. So this is the tip of this rod, of this ferromagnetic rod. And here's a cell, and there's a bead in here, and then you can sort of see about 50 microns away. And if you turn the current on, it moves a little bit, and then this is calibrated and so on. You get a step response, and you can calculate this G prime, G double prime in a fairly small frequency range, but good enough to get a reference. So that's and you can also do that with optical tweezers, and this is something that or actually a former postdoc of mine, Daisuke Mizuno at Kyushu University has done, and we had a paper on that a couple of years ago. So it compares well to other measurements, and I talked with Timo. I think this was in the same ballpark. So you get a good estimate or reasonable estimate for the shear moduli G prime and G double prime from this additional experiment. And then you stick that into your fit. Again, we do the global fitting with this two-dimensional sheet for all the different Qs. So here we collect a couple of different Qs for how many microtubules there was, but a couple of 10 microtubules or so, and with the respective harmonics and higher modes. And we use that at first to just pull out a number for the bending stiffness and the force spectrum. But what's relevant what we were after is, of course, the bending stiffness of the microtubules. Now, I should say the bending stiffness of the microtubules is kind of still a disputed number, and I still have a bet with Joe Howard for a case of beer that if it's 5 millimeters or 1 millimeter, so he measured way back that it's more like 5 millimeters in thermal equilibrium, and we saw something less. But it's still an open question, and it probably has to do with defects in reconstituted microtubules. So if you isolate microtubules from brain, for example, and reconstitute them, you probably get defects. And you get also, and that's something I'm going to come back to, you have many post-translational modifications in microtubules in cells. And if you isolate them from some tissue, you get a unknown mix of all these things. And so it's probably a bit of a mess, and they're kind of sensitive structures. And so the in vitro data have to be taken with a grain of salt. But that makes it even more important to measure these properties in cells. And so that's the main reason why we did that. So this is what we found in the cells, and that's actually sort of in the middle of the range that people found in vitro. So it's not totally crazy what people found in vitro, and also not totally crazy what we find here. So that's reassuring. And so the last thing we did then is to look for a change, and that is, I guess I have still a minute or so. Before doing that, Tango also figured out a different way of checking on his results. So what on actually the rheology results. So what we know is that if you put a point force on a filament in a viscoelastic environment, you get a deflection that has a particular shape, and this shape can be characterized by a characteristic length, and that length is just this fourth root of the bending stiffness if it's a homogeneous bending rod, divided by the elastic response of the medium, which is an energy minimization. So you just distribute the elastic energy into the bent filament and the surrounding medium, and if you minimize the sum, you find that length scale. You also know the shape. So this particular shape is expected, and so what he did is he looked at cases where there was a large deviation from the straight shape of these microtubules, assuming that this was probably caused by a myosin motor that was fairly close by and pulling really hard on this particular microtubule and then letting go again. And so he then looked at the shape of the static shape of these microtubules when they were deflected by a large amplitude and just fitted them to that function. And that function, of course, then through that L, it contains the G prime. And so he used that to check on the magnetic bead experiments. And it turns out that actually, see, I think it was the next slide. Yeah, that works out pretty well. So the shape, first of all, fits pretty nicely. I can show you more, but this one is, of course, the typical one that looks the best. So this fits that, but yeah, I guess this one here really well. And if you compare the modulus in the control cells with the results from the rheology experiments, you can see the dotted line is of course just one number for the G prime at zero frequency, sort of zero frequency here. This was not very frequency dependent anyway, with the other results. And we also did this, or Kengu did that after basically destroying the actin. So you can put drugs in that more or less depolymerize the actin, like trunculin A in this case. And when you depolymerize the actin, probably not completely, but partially, you see a steep drop of the G prime, which is of course what you expect. So the bending length gets quite a bit larger, and the corresponding G prime gets quite a bit lower. So it was kind of a sanity check. But the last thing I want to show you was something where we hopefully learned a little bit about real biology. So it turns out these microtubules, as I mentioned already, have a lot of what's called post-translational modifications. Now, it turns out those modifications mostly happen at the C terminus of the microtubules. The C terminus is about 20 amino acids that are intrinsically disordered. So it's one of these, it's not going to phase separate here, but it's one of these interesting parts of proteins that nobody really knows what they're good for. But in this case, they decorate the surface because the C terminus sticks out to the outer edge or outer surface of the microtubule. And these are quite charged, so negatively charged already. But there's a whole bunch of modifications that particular enzymes perform on these C terminal tails. And the polyglutamylation is one of them, where you have a lot of glutamic acids, up to 6, added to an existing glutamic acid. And these are also negatively charged to basically increase the negative charge density. It has been shown that this is important to regulate kinesin 1 motors. And it also has been shown that this modification is prevalent in axons, for example, and it's performed in cells in places where the microtubules have to be stable. So it's believed to be in a sort of very fuzzy way to be stabilizing. And so this is the glutamate ion. So you can see there's these charges, and then the negative, it's in the end, net negative charge at pH 7. Antonina Ronetchak is at NIH is a specialist in these post-translational modifications of tubula, and we worked with her. And she gave us the plasmid for a particular enzyme. It's called the tubulin tyrosine ligase like 6 enzyme, TTLL6 short. So more than 3 letters. Usually there are always 3 letters. And it's conjugated with YFP. So we can see it, and you can check if it's expressed in the cell. So you transfect the cells, it's like methods to get the plasmid into the nucleus, and then it gets expressed. And if it doesn't get overexpressed, it's sort of you believe that it's sort of functioning properly. And you can control that by imaging, by fixing and staining the cells. So here, this is the YFP signal from the expressed enzyme. This is the alpha tubulin antibody signal, and then you also can get an antibody that's specific for glutamylated tubulin. So you can check that tubulin is actually largely glutamylated in these cells that express this extra tubulin, the TTL6 enzyme. Overexpress it, I guess, of course, in comparison to what they normally do. And if you then do the whole 9 yards procedure I showed you before, with looking at the fluctuations of the microtubules and pulling out the bending modulus, it turns out to be quite a bit more. So this was the control, and these are the TTL6 expressing cells where it's about a factor of 2 more. Now, within the noise limits, it's probably just barely significant, as you can see here, but it shows you that you can actually go into the real cell, the living cell, and use these fluctuations to check for these mechanical properties of microtubules in cells. And I should say you can also do that, of course, for other elongated objects. So we have done it to microtubules, but you can imagine doing it to mitochondria or the endoplasmic reticulum or active filaments are kind of hard to image, but well, as I showed you before in special super resolution, you can also image those. So it's a method that avoids putting any extrinsic probes into the cell, and it just uses what's there and gives you some information on both the filaments that they're looking at and that changes. Especially, I guess it's going to be easier to look at changes when you change some external parameter. And also, of course, information on the embedding environment. So with that, there's a whole bunch of conclusions here, because I guess I gave this, started with this broad overview, hopefully was useful for some of you, about microrheology and its whatever 30-year history. So you use these small particles, and that's good to study soft materials at high frequency with high bandwidth. Then when active matter came in, you can use various methods to characterize the non-equilibrium fluctuations, and also to check if something is equilibrium or not. So you can look for, you can use the fluctuation dissipation theorem to quantitate the amount of non-equilibrium, and you can also work with broken data balance analysis. And Chase Bruners was very much involved in this initial study, and he has been pushing this further to actually also quantitate something about the driving forces from looking at the vorticity in the space spaces. Then the last part was all about these filaments. You can use them because they get into anything, like especially the carbon nanotubes. You can use them as stealth probes. They're multi-scale, something within a range. And of course, what I find most exciting, you can use native structures in cells. You could even, if you want, generalize it to membranes. So it doesn't have to be one-dimensional, but I guess one-dimensional is easier to image, to learn something about the activity of the cells and also these filaments of these systems. So this is work that has been going on for many years, of course. So the most recent work, actually the work that was still done in Göttingen was the broken detail balance work and then some of the cell fluctuations that Nikta was very much involved in, and Chris Battle, a grad student at the time. Kengo joined the lab as a postdoc already back in Göttingen, then moved with me to Duke, and he's now a postdoc at UNC, looking for jobs actually. He has done all that recent work I told you about. Anfam was a postdoc who has moved on to Chicago, who helped with set up the magnetic tweezers. Sufi was a postdoc who has moved back to India, who did the cell cultures. He's a cell biologist. And Bezat has still just finishing his PhD thesis in Duke, is work on cell mechanics. And there has been a long-time collaboration with Fred McIntosh on the theory side. More recently, the tissue pictures I showed you in the beginning are kind of showing our new collaborations with developmental biologists, mainly Dan Kier, but also Stefano D'Italia at Duke. And Michael Rubinstein is, of course, close by, so we always probe him for theoretical insights. And of course, I mentioned already Antonina's lab, so they provided the enzymes for the modifications. And Deiske was a postdoc back in Amsterdam, who's now a professor at Kyushu University, who's the chair of the department even now. So yeah, students, when your students become chairs, then I guess you feel old. When they retire, it's even worse. But so he was the first one getting into this active microrheology and active systems way back. So I hope. Oh yeah, and sorry, I should mention Chase. I did mention Chase. So he was actually in Aspen. We were sitting together and looking at experimental results, and then figured out that we can use broken detail balance. And Jennifer's lab was involved in Flagella and Joe Howard's group as well. Thank you very much for your attention and maybe questions. Guess nobody's picking us out, so there's no lunch right now.
So for the microtubule in a cell, when you add the source, what you're saying is that it buckles. The microtubule, I mean, the formula you showed is just that, that it buckles the microtubule, and the confirmation is that of a buckle microtubule. That's true.
So buckling, strictly speaking, would be a force on the ends, right? And so
Yes.
Cliff, for example, has done these experiments when cells hit the cell boundary, they buckle, and then you get that same length. But you also get the length that you have a transverse force. And so experimentally, we stayed away from the cell boundary so that we can sort of, if we look for buckles that happen sort of not near the end of the microtubule, but sort of in the middle. Now, it was, of course, bound into a network, and so it was a bit tricky to avoid, to be really sure that there are no axial forces.
There's no effect on the fluctuation, the environment. So.
Well, that's why we went to large deformations. Like if you find one that looks kind of isolated and has a really large deformation, then you assume that there's one dominant Meisen motor that pulls it. At least, or maybe two, but something very localized to the tip of that bend. And the proof is in a way in the pudding. But if the shape really fits that shape, there's sort of a consistency check on that. So it was, the whole thing was more like a consistency check anyway. So I don't think I would use that method. Well, in a way, I guess it's related to Timo's method of looking at fluctuations, if you remember from last week. I mean, they were doing it in this more sophisticated way, looking at all amplitudes. And then here we just focus on the large ones to get rid of all the other stuff. Yeah, bro.
So one thing which I had, Question we've been studying this model that Fred and Alex looked at with the stuff, but that was back in the journal and others. There is no explicit equations in that model governing the motion of the universe. It's in some sense, it's in the additive active noise. Sorry.
In our case.
Well,
or
in Fred and Alex's model.
Oh, that model.
Model. So the question is that, we are of course investigating it, but wanted to ask your opinion whether you think that having an explicit dynamics of these motors that can attach, detach, then pull this, and from where you generate your correlation function spectra, that function CFF divided by 1 plus tau, tau the whole square, that thing, that.
I mean, you have, of course, these are not kinesins, so not dyneins that move in a processive way. So there are little dipoles of polymerized anti-parallel myosin, and they bind for these 5 to 10 seconds. And while they bind, they exert force to two sides. So of course, there could be a net displacement of the motor depending on how it's connected to the actin network. But we assume it sort of just more or less stays put and contracts. And of course, we also assume that the amplitudes are not humongous. You saw that it could be a couple of microns, but most of these fluctuations, well, I guess I should be careful. We also looked at this distribution of displacements, and it has tails that are non-Gaussian and so on. So you can get deeper into that, but in the first approximation, you assume they don't have very large amplitudes. They have a time correlation, and they basically don't move around. And of course, that's maybe more important. They don't create large-scale collective flow patterns. And of course, when you connect to, say, the Swann-Virus models, also where these myosins are working in kinesins are working in a dense network, then they have these collective flows and stuff. But here the system is fairly strongly cross-linked anyway, and we assume, at least in the cells we looked at, they don't create these collective motions. In other cells, in XL and oocytes, it's very famous, of course, that you get these very large-scale connective flow patterns. That would be different there.
Is there any studies of correlated fluctuations of nearby microtubules?
Not that I know of. That's a good point. I mean, I guess if I were to speculate, I would think. I mean, you sort of know roughly the range, the force range of the dipole, so you should decay with 1 squared or so. Or 1 cubed. I guess it could be near field, so the dipoles are fairly large. So that I would think might dominate. You were thinking about hydrodynamic correlations, or between the microtubules?
Cytoskeletal network that before one and
yeah, there should be coupled to the actin. I would think so, more than via hydrodynamics.
Yeah.
And yeah, it's a good point. We never looked at that, so it should be measurable. If you, and we did actually know, not in microtubules. We looked at that in the actin system, in the in vitro system. We looked at when we had many beads in there. We looked at the pairwise correlations of the beads. And we found there was a transition from positive correlation to negative correlation. And we used that to estimate the average distance between force dipoles. So if you're in the range of 1 force, in the near field of 1 force dipole, you would get positive correlation of 2 beads moving together. And if the force dipole is between 2 beads, then they would move this way. So we could see that. But we haven't done the same analysis for the microtubules in the cells. That could be interesting, yeah. But there's imaging from Jennifer Schwartz's lab where you can actually see the myosins. And they're couple microns, maybe 1 micron apart, so they're pretty close together. So it might be hard to get enough data, between in the near field of one motor, but it could still be interesting. But then, of course, I think the motors also start cooperating and have correlations in their activity as well. So it gets complicated.
Yeah, I wanted to say that actually, what now turns out to be characterize is actually very similar approach where you can use it after the full active driving with active counting particles or cell model or cell sheet model, where you have no correlation between the activity between particles of persistence. And so you can do similar breaking of the partition and response functions
Yeah, I mean, any active system should of course break detailed balance, and also the fluctuation should not obey the fluctuation.
Yeah, but you can actually, I can show you, but it turns out it's actually something really similar that's there as well. But
So in terms of the spectrum of fluctuations,
of the spectrum, we can actually using this in further mechanics.
I see.
To measure different things and in further mechanics of the sheet, you can make the same assumption that it's mostly elastic. as well.
okay. Yeah, we should look at that because I've missed that analogy so far.
And I didn't realize it. I didn't realize until that now.
Okay.
How close it is.
Yeah, let's check.
Yeah.
Lunchtime?
Maybe lunchtime.